Hey guys, these are our notes about population versus sample for Unit 1. Once you're done, you're going to go put them into your digital notebook on slide 19 through 22. So at the top of your paper, you can go ahead and put your title, Notes 1.2.1, Population versus Sample. So this is our first notes from Lesson 2 of Unit 1. First, we just have a bunch of vocabulary to go over. There's not really any equations or anything. So first off is population. Population is just all people or objects that are of interest in a data collection and an investigation. Then we have parameter. Parameter is just your numerical value that represents your population data. It could be a proportion, a mean, a variance, standard deviation, all those different things. So it's just a numerical value. Representing the population. We also have a sample. So a sample is just a subset of the population. And then our last vocabulary word is just our statistic of interest, which is just our number that we use to summarize or represent something about the sample that we drew from the population. So it's just a number used to summarize or represent something about the sample that was drawn from the population. So we have some symbols that we're going to use. So our population symbols, we use mean as mu, and we use standard deviation, we use sigma. And then if we're talking about the sample, for mean, we use X bar. And for standard deviation, if it's a sample, we use S. Let me just say S. So this is going to go into your digital notebook. We're going to go do 4 examples. So you're going to need to grab your workbook, and we're going to start on page 47. So grab your workbook. We're going to be on page 47. Example 1 says Adam rolled a 6-sided die 4 times and obtained the following results: 5, 5, 3, and 4. He computed the mean of the 4 rolls and used the result to estimate the mean of the population. Identify the parameter, sample, statistic of interest, and then calculate the identified statistic. All right, so parameter. Parameter means all people of objects. So we're talking about rolling a dice. So the parameter would be all of the dice rolls ever. So it would just be the mean. Parameter is the mean of all dice rolls, or mean of all rolls of any 6-sided die. Our sample, right, we can't have the whole parameter, we can't have all rolls ever, right? So we just have Adam's rolls. which were, what's my little bracket brace, 5, 5, 3, 4. And then our statistic of interest, what we're interested about Adam's roles is basically just the mean, right? We were trying to find the mean of Adam's roles. So our population is all of them. So our parameter would be the mean of all of roles. But we don't have all roles ever. We have a sample that is Adam's roles. So the parameter and the statistic of interest are going to be kind of the same, except for the statistic of interest is based off of the sample and the parameter is based off of the population. So now it wants us to calculate the identified statistic, which is just the mean of Adam's dice rolls. So we're going to go ahead and find the mean. He could roll a 5, a 3, a 4. So we add those together and divide by 4. So 17 divided by 4 is 4.25. And that would be X bar because it's a sample mean. So X bar is 4.25. So again, the parameter and the statistic of interest, they're both the mean, but the parameter is based off the population and the statistic of interest is based off of the sample. So we can't have all dice rolls ever. We just have Adam's 4 dice rolls, which isn't even that big of a sample size. Normally you'd want more. All right, let's go to example number 2. Example number 2 says high levels of blood glucose are a strong predictor for developing diabetes. Blood glucose is typically tested after fasting overnight, and the test result is called a fasting glucose level. A doctor wants to determine the percent of his patients who have high glucose levels. He reviewed the glucose test results for 25 patients to determine how many of them had a fasting glucose level greater than 100 milligrams per deciliter. He recorded each patient's fasting glucose level in the table as follows. So what we need to do is we need to identify the population, the parameter, the sample statistic of interest, and then calculate the percent of patients with the sample fasting glucose level above 100. Okay? All right, so first we need to identify our population. Our population is like everything, and then our parameter is what we want to know about, all people, all everything, all objects, and then our sample is what we actually collected, who we actually collected, or what we actually collected, and the statistic of interest is based off of that sample. Okay, so first is our population. So we're talking about this doctor, right? Doctor wants to determine the percent of his patients with high glucose levels. So the population is just all of the doctor's patients. So our parameter, all right, pop and para for population parameter. Our parameter is he just wants to know percentage of his students who have, or not students, percentage of his patients who have high glucose level. So parameter is just percent of patients with high glucose levels. All right, so then since we can't get all of the doctor's patients, he can't collect data on all of his patients, right? We don't know how many patients he has, but I'm sure it's hundreds. So he's going to just get 25 patients, okay? 25 patients, that's his sample. And he's going to go ahead and find his percent of that sample that has high glucose levels. So that's his stat of interest. So our stat of interest is just the percent of sample patients with high glucose levels. So that wants us to identify population, parameter, sample statistic, and then calculate the percent of patients that have a glucose level above 100. So I'm just going to go through and I'm going to, see how many are above 100. So I'm just going to highlight all of the numbers that are above 100. And then I'm going to go ahead and just count how many there are. So I have 1, 2, 3, 4, 5, 6, 7 out of, we know there was 25 patients, so 7 divided by 25, grab my calculator, I get 0.28, and then to make that a percentage, because it wants a percent, and it's going to be 28%. So 28% of our patients have high glucose levels. All right, so example 3, it says data collected by the National Climatic Data Center from 1971 to 2000 was used to determine the average total yearly precipitation, so rainfall, for each state. The following table shows the mean yearly precipitation for a random sample of 10 states and each state's ranking in relation to the rest of the states. Where a ranking closer to 1 indicates a higher mean yield precipitation, use the sample data to estimate the population of total rainfall in all 50 states for a 30-year period from 1971 to 2000. All right, identify the population parameter, sample, and statistic of interest in this situation. All right, so first off is our population. So think big. What are we looking at? We're looking at states, right? These are states. So we're looking at population will be just all 50 states. And then the parameters, what we want to know about all 50 states. So what we want to know is we want to know the total rainfall for all 50 states from this 30-year period. Okay, now we're going to think smaller, right? So population parameter, we think big. Then for sample and statistic of interest, we think a little bit smaller. So for our sample, we weren't able to take all 50 states, so instead we just have these 10 states, right? Sample of 10 states. So 10 randomly selected states. And what we're going to do is we're going to first have to calculate for our stat of interest. If we want to find the total rainfall for all of the states, we're going to have to go ahead and find the average rainfall. Okay, some are going to rain more than others, right? So we're just going to find our average rainfall for one state, and then we can use that to try to find our parameter, which is all the states. All right, so we got our population, our parameter, our sample, our statistic of interest, and now we're going to go ahead and find our rainfall. So we're going to go ahead and first find the average rainfall. So I'm going to add up all of these numbers right here. Use my calculator. So it should hopefully, as long as I added it all up right previously, it should be 320.6. So we add them all up, and then we divide by how many states? There's 10 states. So that means that on average, it's about 32.06 inches per year. Okay, so we average them together. Some are going to get more than that. Some of them are going to get less than that, but on average, 32.06 inches per year. All right, well, there's 50 states, so we're going to have to go ahead and multiply that times 50 states. So 32.06 times 50 is 1,603 inches per year for all of the states, because this is for just one state. So this is how much in there, with all 50 states in 1 year. And then we have to multiply it by the 30-year period. So then I'm going to multiply it times 30 years. So 1,603 times 30 gives me 48,090 inches. So that's how much rainfall that we got in that 30-year period. In all 50 states. Okay. All right, last example. So this would be on page 49, example number 4. It says, for her math project, Stephanie wants to estimate the mean and standard deviation of the points scored by the home and away teams for the National Basketball Association, NBA. She randomly selects one home game and one away game for each of the 16 NBA teams during the 2012 season and records their scores in the table. Use a graphing calculator to estimate the mean and standard deviation of the points scored by the home and away teams of the NBA. Identify the population, parameters, sample, and statistics of interest. Okay, so first I'm just going to do this part, and then we'll go through and we'll talk about finding the mean and standard deviation using a graphing calculator. All right, so first we want the population. So think big, population, thinking big. These are all of the teams, right? We want all of the teams, and we want all of the home and away scores. So our population, what we're looking at is all NBA home and away scores. Our parameter that we want to know about these games is we want to know their mean and their standard deviation. So it's just the mean and standard deviation of points scored at home and away. All right, now we think smaller, okay? We don't have all of the games ever played. We just have a sample of games. So it says right here that she took one home game and one away game for each of the 16 NBA teams. So our sample is that, just a randomly selected one home and one away game, or one away score for each NBA team, right? For each of 16, well, each, I'm gonna say 16 NBA teams. Are there more than 16? You guys can fact check me. All right, so then our statistic of interest is basically the same thing as the parameter, but not as big, not of all home and away games. It's just the mean and standard deviation of sample games. So what we're going to do is we're going to go ahead and calculate the mean for home and mean for away, and then standard deviation for home, standard deviation for away. So I know the table looks kind of weird, but these are your home scores. There's 16 teams total, and these are your away scores, so they're not all like next to each other. All the yellow ones are the home games, all the green ones are the away games. So we're going to go ahead and get our statistics of interest. All right, so in order to calculate them, you'd have to add them all together and then divide by how many there are. That's how you find your mean. Then you have to find standard deviation. Remember, that's where you take all of the data minus the mean, subtract them, square them, add them all up, divide by n-1, take the square root. That's a lot of work. So instead, we're going to use technology. So Desmos, our graphing calculator. I already typed in all of my data. So at the front over here, I have it says the mean, and the first numbers are from all of the, oh no, 97, 87, I accidentally deleted some, comma, 106, hopefully that's right. Okay, I think I got them all. I accidentally was hitting delete instead of like the arrow. Okay, so the way that you can find the mean using technology is you literally just type in mean, parentheses, and then just whatever your data is. So the first one is for the home games. So the home one, we're just gonna round to the nearest whole number. So 102 is the mean for the home games, and then the bottom one is all of the away games, and the score there is, we'll round up to 98. So the mean, we'll do the home games first. The mean, which is X bar, was 102. And for the away games, the mean, which is X bar, was 98. Then we're going to find our sample standard deviation, S. So the way that you can do that, still using Desmos, I can use exactly what I had before. I'm just going to delete the word mean, and then I'm just going to put STDEV for standard deviation. So I'm just going to delete mean and just put STDEV for standard deviation. So the standard deviation for the first one is 11.18, so I'm just going to do whole numbers. It's 11. Standard deviation for the away games is 11.4, which still also rounds to 11. So both of them have a standard deviation of 11. So again, just a review, population, think population parameter, think big, right? Population is all of everything, everyone. Parameter is what you want to know about all of those people. And then your sample is just who you were able to collect data from or what you were able to collect data about. And then statistic of interest is just the same thing as a parameter, but about the sample instead of about all of thinking big. We use the statistic of interest and we try to summarize that about everything. So we would say, you know, I can't get every game ever, but on average, you know, the home score is higher than the away score, but they have the same standard deviation, that kind of stuff. All right, so put these in your digital notebook and we're done.